Hello, everybody. Um, I thought I'd give us another worked example just to see how it goes. So, um, what we have going on here is let's get the highlighter out. Two people grab the same toy, the last of its kind in the city, the happy troll with the kitten attachments. So each arm acts like a spring, with the arm with the kitten having a larger resistance to stretch. Okay, so we build our troll that's being tugged on. And this is the one with the fluffy kitten on it. Um, so this is going to act like a spring this way, and this one's going to act like a spring that way. So what we're looking to find is a specific equation of simple harmonic for the toy, which has a given mass and each arm is stretched 75 centimeters. Alrighty, so let's see how much of that information we actually need. First, we'll go to our final exam sheet, and then it will point out and give us the general equation for simple harmonic motion, which is x as a function of t will be a sine omega t plus phi, where omega has to be equal to the square root of k over m. Maybe. Oops. I mean, how do we know if this is even true? It's a good question. So, first thing we're going to do is check this equation of motion against the forces. Duh, I don't know why that took so long to figure out. So we're going to sum the forces, get an acceleration. For the forces, I'm going to have big K x, and let's make that one this guy pulling this way, and the other one little kx for the force going that way. We can pull the x out, and you'll get big K minus little k. Equals MA. Now you're going to have to hold on for a second to make sure we got the sign notation right. Because if we've pulled it towards the kx, if that force is our largest force, and we're going this way with the x, then this force is a compressive force. So this is kx in the positive direction, so this has to be negative kx. And then the little kx, when we go this towards the big kx direction, gives us a force that is it's positive in the negative x area, so the kx here has to be positive. A little confusing, I know. That's why I made a video about it. And what we've come up with is, dribbling. We've come up with the general form of the equation. That x looks like something, has to be negative, mass dx as a function of t over t. So this is going to be little k minus big K. And the reason I have a minus sign out here is we know little k is smaller than big K, so this value numerically is going to be negative. So we're in good shape right now. Okay. So we now have the correct omega. Omega is equal to the square root of little k, negative little k plus big K over the mass of the toy. Now we have to think about how the toy itself is being pulled apart, so that at time equals 0, when we think about this, we have an even stretch, and that's the important part, is it begins in a stretched position. So when we think about the initial conditions, we would expect something to begin stretched, collapse down, come back up. So we would expect then that phi will be pi over 2, because this is a cosine function. And we can check all this because the checking process says put in a value x at time t equals 0. And we have a sine 0 plus v. And we wind up with v as a function of time equals 0 equals a omega of 0 plus phi. Now the nice part is the people are fighting over the doll, which means the doll isn't going anywhere. So we can assume this to be 0. And we get A omega cosine of phi. The amplitude cannot be 0. The omega cannot be 0. So that means this term here is equal to 0. So cosine of phi equals 0 when phi equals pi over 2, 3 pi over 2. This is when I'm getting a little concerned that I'm not remembering it correctly. And then I say to myself, I don't have to remember this correctly. All I have to do is put pi divided by 2 into my cosine function of my calculator, and it didn't like that. That's not very nice. Let's try that again. Cosine of pi divided by 2 gets me 0. Alright, so I do have the right spacing. So we now can use this same information here, because we know what phi is equal to, and plug it into here, where we know each arm is stretched 75 centimeters. And we've chosen the middle of the toy to be the x-axis. So that means that at time t equals 0, I should have 0.75 meters in place. That's equal to A. And then the sine of 3 pi over 2, and this brings this pi over 2 value to 1. So A is equal to 0.75 meters. So the specific equation is x as a function of time is equal to A, which is 0.75 meters, times sine of omega, which we just said was big K minus little k over the mass and t plus phi. So we know phi, it's pi over 2. If we felt like taking this the next step further, I might as well turn that into the cosine. Big K 180 minus little k 120 leaves me 60 inside and 0.25 kilograms for the mass. So I'm going to get the square root of 60, 0.25 t plus pi over 2. Oops, we got rid of that already when we changed the cosine. 0.75 cosine of, let's see, clear, 60 divided by 0.25, second function, square root of the answer, and we get 15.5 t. And that's what's meant by the specific equation. So, to solve the specific equations for motion, it comes at us in 3 steps. First, we're going to use Newton's second law of motion as our starting principle, and it will give us an equation of motion. Then, what we'll do is, we'll check this green solution out next so that we can get an accurate omega from the force discussion. And then lastly, what we do is we plug in the initial numbers. We start with our Vx and Vy. We plug in our specific numbers to get our unknowns. So this step was all about find big A and phi. This step here is to find omega. So we use forces, we figure out what omega has to be equal to. Then we can use the given information to find our values of A and Q. And then once we have all that information recorded, we can come over here and say, I've got this specific equation because I took all the given information, all of these guys, we'll keep it as this, all the way through these steps down to the last one. So it's a multi-process problem, but it's transparent in the sense that it has easy steps to follow. You do the forces, you fit to the equation of motion, you put in the variables that define the problem, and then you'll get a specific equation. So, hope that helped, and yeah, ta-ta.